Hello everyone, my name is Han Mao. Okay, welcome to the second talk of the seminar series, Information Theory in Singapore, ITIS. And welcome to Virtual Singapore. All right, so last week we saw the view from Mehu's office, and today I'll present to you the view from Chai Kui's office. Okay, well, this is not the exact view, but a close approximate. Okay, so in any case, this is Singapore's Changi Airport, which is situated quite near Chai Kui's office. And well, like most airports in the world, this airport is rather quiet during these unusual times. And I hope these strange times will pass soon and you can visit this airport in person sometime soon also. So again, the Information Theory in Singapore, ITIS seminar series is organized by a team that includes Mehu from National University of Singapore, NUS, Kui and Chai from SUTD, Singapore University of Technology and Design, and me from Nanyang Technology University, okay, NTU. And our aim is to promote, advocate, and spread the joy of coding theory and information theory within Singapore and around the world. So we have 5 talks in this series for this year, and today is our second talk. Now, before we get going, let me address a few logistical issues. Please keep your microphone and video muted for the duration of the talk. And if you have questions, you can post them here to the group chat, and Venkat will keep a lookout for it. We'll address questions in the Q&A. We also address the questions in the Q&A session at the end of the talk. And so, with that, it's my great pleasure to introduce our speaker, Professor Venkatesan Guruswami. Now, Venkat is professor at the Computer Science Department at Carnegie Mellon University and the director of the PhD program. He received his PhD from the Massachusetts Institute of Technology in 2001 and was a Miller Research Fellow at UC Berkeley during 2001 to 2002. Now, before I read his long list of awards, let me share a little incident, or rather a conversation that I had with my student. So basically, my student was planning to start writing his thesis. And as usual, he asked me, like most students, he asked me if there's a guide or writing style to follow. And of course, Venkat's doctoral thesis immediately came to my mind. So I Googled least decoding of error correcting codes and clicked on the first link and showed it to my student. Then my student gave me a very puzzled look. Isn't this a published book? Okay, now you see. The ACM Doctoral Dissertation Award is awarded annually to the author of the best doctoral thesis in the whole of computer science and engineering. And the best dissertation is usually good enough to warrant publication as part of the ACM book series. And you probably guessed it. Venkat's dissertation won the award and hence is published by ACM as a monograph. And of course, a much longer list of awards will follow for Venkat. Venkat is a fellow of the ACM and the IEEE. He was an invited speaker at the 2010 International Congress of Mathematicians and gave a talk on the topic of mathematical aspects of computer science. His other honors include the EATCS Pressburger Award, the Packard and Sloan Fellowships, a Google Faculty Research Award, the ACM Doctoral Dissertation Award, and an IEEE Information Theory Society Paper Award. He was recently named a Simons Investigator in the theoretical computer science by the Simons Foundation. Now, besides all these awards, okay, Venkat has always impressed on me as one with a very sharp and extremely clear mind. Okay? This is exhibited in both his writing and talks. And so today it's my honor to have him as our speaker. The title of his talk is Arıkan meets Shannon, Polar codes with asymptotically fast convergence to channel capacity. Venkat, please.
Thank you very much for the very kind introduction, Hanmo. Hope everyone can hear me. So yeah, I was at NTU for my sabbatical, I guess now 3 years back at this time I was there. It was one of the most memorable stints I had, and I have really fond memories of both the university, the campus, and Singapore and the general area in general. So it's a pleasure to sort of reconnect back and talk to folks in Singapore, even if it's only virtually at this point. Okay, and thanks to everyone for tuning in. I know there's a lot of Zoom fatigue and one more talk and other things to go to is always, everything seems harder these days. So I particularly appreciate people tuning in. Yeah, today I'll tell you about polar codes and how they, in a certain sense, achieve this long milestone which Shannon had proposed long time back. And this is joint work with Andre Rizzano, who's a PhD student at CMU, and Min Ye, who's currently at Tsinghua Berkeley Shenzhen Institute. All right, so okay, so I'll start with the broader context. And so we have a party who wants to send a particular a message to another party, and then so let's say this input symbol is X. So for some reason the thing doesn't work. Just 1 second. Okay, I'll just use the thing. Okay, but the channel is noisy, so it gets the symbol X gets distorted by noise, and it's received as another symbol Y, which is related to X according to some probability law. So if you send X, there is a probability distribution on possible outputs, which is denoted by W given X, and that's what Y receives. And this is just a stochastic channel, and we'll be considering the memoryless setting, which means if you send n symbols on this channel, the action of the channel on the different symbols are independent of each other, and that's memoryless. We will also be considering only the binary input case, so X is just a bit. So you put a bit into the channel and out comes a random output. And we will also be considering the discrete case, which means the output alphabet is some finite set. So for example, here is an example channel. The inputs are 0, 1, outputs are A, B, C, D, and each row gives you a probability distribution of what you can receive when you send the particular symbol. And we will also be interested in the case of symmetric channels, which simply means that in this case, for example, you can see that if you send the columns can be paired up so that if you flip 0 and 1, you get the other column. So this is sort of symmetric with respect to flipping 0 and 1. The output symbol A becomes output symbol B. Okay, it's not so important, but this is because for such channels, you can hope to have linear codes which achieve capacity. So we'll restrict our attention to these channels, which are called BMS channels, binary memoryless symmetric channels. And these, of course, capture some very interesting and well-studied channels, notably the binary symmetric channel, where you send the output alphabet is also a bit, but then it is equal to the input bit with probability 1 minus P, and it's flipped with probability P, where P is the crossover probability. Okay, there's another channel, the simple channel of the erasure channel, where there are no errors, but with probability delta, the bit can get erased and you can get a question mark. So both of these are examples of BMS channels. And what can you do on these channels? Well, you would like to transmit messages reliably. So clearly, if you just send data in the clear, that can get corrupted, and there's no way for you to figure out reliably what was sent. So you do error correcting codes. So you take your message and you encode it, so if K symbols long, and encode it into a longer N symbol code word. In this case, it'll just be an N bit code word. And then the output will be, the channel will output a vector y1 through yn, and the goal of the decoder is to take this output and figure out what the original message was, and hopefully m prime equals n. And we will be interested in linear codes, where this encoding function is simply going to be a linear map, which maps a k-bit vector to an n-bit vector. And so K will be the dimension of the code and N the block length. All of this is standard terminology. And of course, the most important parameter for us will be the rate or the information rate of the code, because we would like to not add too much redundancy. So we would like this ratio K by N to be as big as possible. Okay, so and okay, so what did Shannon prove in this setting? Shannon proved that for every channel, there is a precise number called the capacity of the channel, which in the case of BMS channels is between 0 and 1, so that you can have linear codes and some decoding algorithms, which allow you to communicate at any rate which is less than the capacity. And on the other hand, there's also a converse, in the sense that the Shannon limit is an absolute information theoretic limit. If you try to exceed this I of W, then you will invariably make a mistake in communication. An asymptotic rate means that you send n symbols or n bits on the channel and then try to communicate in that roughly I of W times n information bits. So K by n approaches I of W as n grows to infinity. Okay, so it's an asymptotic statement, but you can actually get more quantitative versions of this as well. So in fact, it is possible to achieve a rate of capacity minus order 1 over square root n, Or put another way, if you're within epsilon of capacity, then you can communicate with the error probability, something like 2 to the minus epsilon square n. And this is also known to be the best possible. There are strong forms of the converse which say that the inverse square root convergence which you get is really the best you can hope for. Okay. So that's great. So we know exactly the limiting rate, and we also know how well we can approach the limiting rate. So everything seems to be very nice. But of course, the problem is that Shannon's theorem is non-constructive. So Shannon showed that if you take a random linear code of rate approaching capacity, and then you do maximum likelihood decoding, which is prohibitively expensive, exponential time, then you achieve reliable communication. But of course, the challenge is we would like to not have random codes. We would like to have explicit codes. And then we will also like to have efficient algorithms to perform the error correction. Okay. Note that if your code is linear, encoding map is trivial or easy because it's just a linear transformation. So the main difficulty is correcting the errors and doing decoding. So this has been the big challenge. And of course, so if you know, the message of this talk in just one punchline is that we give a constructive and quantitatively strong version of Shannon's theorem. So in particular, for any BMS channel, we give a polynomial time construction of linear codes which have efficient decoding algorithms. And further, the rate approaches capacity at almost the optimal speed of 1 over square root the block length. Okay, so these achieve capacity in the limit, but they also have good asymptotically at least finite length performance because of this optimal speed of convergence. Okay, so I'll maybe just leave that for a second so people can look at it, and please feel free to stop me at any time if you have any questions. So that's really what I will try to tell you the story of the journey towards this result. But really the good part of the talk will be survey or introductory style. I won't assume any knowledge of polar codes or anything. Okay, but to give some context, obviously achieving capacity is a fundamental problem of coding theory. So it's been a long line of work on this. So even way back in the 60s, Forney's work told that you can achieve capacity in the limit, but unfortunately the rate of convergence was rather slow. It was something like inverse logarithmic. So in particular, to get within epsilon of capacity, you need lengths which are like exponential in 1 over epsilon, which is very big. And of course, this is a very practical problem as well. So there are lots of practical schemes which get very close to the Shannon limit, but they do not arbitrarily approach capacity. They do not get within any desired epsilon. And notable examples are turbo codes and LDPC codes. And LDPC codes are, however, known to achieve capacity arbitrarily closely for the special case of erasure channels, but this is not known for, say, the BSC or other channels. Okay, but these are very practical schemes and highly studied and highly optimized. But for us, we want to really achieve capacity arbitrarily closely. So in that context, if you want to get to capacity arbitrarily closely with efficient algorithms, there were two very nice developments in the last decade or so. One, which is the subject of this talk, is polar codes, which Arıkan proved achieves this property. And there's another candidate called spatially coupled LDPC codes, a twist on LDPC codes, which also achieve capacity for all BMS channels in the limit. But this talk will focus on polar codes because one of our focuses is actually going to be to also achieve quick convergence to capacity. Because note that even if you achieve linear encoding or decoding time, this is not useful if the speed of convergence is very low or if the n which you need is very, very big. Okay, so you really need to have understanding of how well you converge to capacity. And how might you formulate this? A good first goal is to have inverse polynomial convergence to capacity. I said that you can get inverse square root, but let's set our goals first and ask, can we achieve a rate which is capacity minus some 1 over some root of n? May not be the square root, maybe some other bigger root like muth root. Okay, and we would like to get this with efficient algorithms. Put another way, this says that if you want to be within epsilon of capacity, then you can have a block length and overall complexity, which is polynomially scaling in 1 over epsilon. So that's the goal. And the miraculous thing is polar codes meet this challenge. And it's worth emphasizing that these are the only codes which are proven to do so currently. Okay, so that's somehow the starting point for this work, that polar codes achieve this this inverse root convergence or polynomial convergence to capacity. And how did this come about? So Arıkan actually proved that the polar codes achieve capacity in the limit of n going to infinity. And in fact, he also gave very efficient encoding decoding algorithms, which have complexity like n log n. And in fact, the decoding error probability can be roughly 2 to the minus root n, swallowed from some follow-up work. So all this is great. The only missing piece was that this work was asymptotic, and it did not tell what is the speed at which you converge to capacity. So a statement like this was not proven, but this was established in later works, one by us with the student Patrick Shea, and another independently by a group at EPFL. So we basically gave an effective finite length analysis of polar codes, and we proved that exactly this statement, that you can have an polynomial convergence to capacity. Okay, or put another way, if you want to operate within epsilon of capacity, you can just take n, the length of the code, to be polynomial in 1 over epsilon. Okay, so that's what we achieved. And this quantity mu, the muth root, if you're within 1 over muth root of capacity, we call mu the scaling exponent, because it really measures how does the length of the code scale as a function of the gap to capacity. And if you recall a few slides back, I said the Shannon's theorem and the optimal thing which you can achieve is mu equals 2. You can get inverse square root, and that's the best you can get. And these polar coding results said that, well, at least mu is finite. So we have a family of codes where mu is finite and which has efficient algorithms. And as I said, polar codes and variants are the only such codes known so far. And there's also a bound of mu, which is, at most 6. But the point is 6 is not 2. So there is still further work to be done, which is what follow-up works did. So our main result stated this way is that we have, for any BMS channel, a code which achieves rate, which is roughly 1 over square root n away from capacity. And the construction of the code and the encoding, decoding algorithms are all efficient. And the decoding error probability, the chance that the decoder mistakes the message for something else, can be driven down to something super polynomially small. Okay, and this result was known previously, but only for the BEC channel, and we generalize it to all BMS channels, which involves substantially many more ideas. Okay, so the punchline is we give explicit efficient codes which have a near optimal scaling exponent which approaches 2. Okay, so that's the punchline. Okay, so before I go into the main body of the talk, I want to at least review. I've mentioned channel capacity many times, so let me actually tell you what channel capacity is for binary input channels. Suppose you feed in a bit to a channel and you get an output. There is a certain probability distribution relating them. So the entropy of the channel is nothing but the entropy of the input bit given the output of the channel, where you assume X is a uniform bit and Y is distributed according to the channel. Okay, and Shannon's theorem in this particular case, the capacity has a very simple expression. It is simply 1 minus the entropy of the channel. The entropy of channel is a measure of how noisy the channel is. How much uncertainty do you have in the input observing the output? So it stands to reason that the higher the entropy, the lower the capacity of the channel. And in fact, it's exactly this inverse relation, 1 minus h of w. So going back to the 2 examples we saw for BSC, whatever output bit you see, 0, let's say, you know that the input bit is equal to that with 1 minus p and unequal with probability p. So this entropy is just the entropy function of p. So the capacity is the well-known 1 minus h of p. This is the binary entropy function. And for the BEC, if your erasure probability is delta, if you get a 0 or a 1, you know what the input is with certainty. So there is no uncertainty. On the other hand, if you get a question mark, because the input bit is uniform, you have no idea what it is, and the entropy is 1. So the average entropy of this channel is exactly the probability of getting delta, which is question mark, which is delta. So the capacity is 1 minus delta. Okay, so for these channels, we would like to get rates approaching these capacity. That's what it means. Okay, so coming to the actual part of the talk, I would like to talk a little bit about polarizing linear transforms, which are the crux of polar codes, and describe polar codes, and then talk about the core issue we have to face, which is how do you analyze how fast these codes achieve capacity. And then I'll talk about some of the ingredients in our construction and analysis. And so I'll spend a lot of the time on the introductory part, and then just highlight briefly where our innovation comes in at the end. Okay, let's talk about polarization. So it turns out if you construct linear capacity achieving codes, those imply something called polarizing matrices. So what are these matrices? So let's imagine an n by n invertible matrix where at the input, I feed in bits which are IID according to the Bernoulli distribution. So each bit is 1 with probability p and 0 with probability 1 minus p independent of the other bits. So these bits at the input are independent, but when I apply an invertible map, my outputs become dependent, of course, okay, or they are correlated. On the other hand, the total entropy on the output is equal to the total entropy on the input because this is an invertible map. Now, expanding the total entropy of all these bits together by the chain rule, we get this fact that the sum of the entropy h of ui given u1 through ui minus 1, which I abbreviate like this, when I sum this up over all I get on average h of p. And the polarizing property says is that on the left-hand side, all these entropies and conditional entropies are equal to h of p. So the entropy is completely smeared. In a polarizing map, on the output side, most of these conditional entropies are polarized to the two extreme values of either 0 or 1. And hence the name polarizing transform. And then you can formally write down what that means here, but really this intuitive description suffices. Okay, so most of the entropies become 0 and 1. And of course, the right fraction about h of p fraction will be 1 and the rest will be 0. There may be a small number in which are somewhere in between. Okay. And Arıkan's remarkable insights is to somehow turn this around. So what I showed in the previous slide is a necessary condition to achieve capacity. But what Arıkan said is that you can actually go back reverse. You can use such polarizing matrices to construct capacity achieving codes. And further, thinking about polarizing matrices, he was able to give an explicit recursive construction of polarizing matrices, and not just in the setting in the previous slide, but even when you have some correlated information about the inputs xi, which in particular will be the channel outputs. Okay, so that's what polar codes are about. So how did he do this? Well, you start with a basic, you want to build an n by n transform, you build it recursively starting with a 2 by 2 transform in this case. So suppose you have 2 bits and there are channel outputs y1 and y2. And of course, you know that both of these have entropies h of w, and the sum of the entropies is 2 times h of w. So you apply a simple 2 by 2 map, and really in this case for bits, for 2 by 2, there's essentially only one non-trivial map, which is this map x1 plus x2 and x2. Okay, so that's this particular map, which is also its inverse. And now once again, because this is an invertible map, the total entropy at the u side is the same as the entropy at the x side, conditioning on the yi's, and we know that this sum is 2 times h of w. And now I can expand this left-hand side by the chain rule. H of u1 given these two outputs, and u2 given y1, y2, and u1. Okay, so far I've really done nothing. So I just write the same thing here. But now comes the main point is that if I now think of transforming by that map and then sending it on the channel, what are the channels which the input bits u1 and u2 see? u1 sees the channel where you observe both y1 and y2. So that's this particular channel where u2 is considered to be a random bit. On the other hand, what does u2 see? u2, if you write down this particular thing, you can assume u2 sees y1 and y2, but you can also assume that it knows u1. Because in the chain rule, when you calculate the entropy of u2, you condition on u1 as well. Okay, so you somehow think of these two random variables. So a channel is nothing but a pair of correlated random variables, an input and an output. So here the input is u1, the output is y1, y2. Here the input is u2, the output is these things. So you think of these two as two channels. So what has happened now is that you have this channel W, you took 2 copies of it with total entropy 2 times h of w, and then you made 2 different kind of channels, w minus and w plus out of it. These are just names of these 2 channels. Okay, so and by conservation of the entropy, the average entropy of these 2 channels is the same as is equal to h of w. On the other hand, it turns out this w plus is a better channel with lower entropy, and w minus is a worse channel with higher entropy. Okay, so you can prove this, in pretty much every interesting case. So what you've really done is that you've taken 2 identical channels and created 2 different channels, which on average have the same entropy, but their entropies are slightly separated. Okay, and you do this by applying a simple linear transformation, which is in this case it's called the kernel. It's a simple 2 by 2 map. Okay, so that's this particular picture. So if you take 2 input bits, you transform it by G2 and send it on these channels, these 2 input bits are going to see 2 different channels, W minus and W plus. And the idea in polar codes or polarizing maps is to apply this recursively. So you have this this baby 2 by 2 map. So what we can do is we take another copy of it, And what we know is that the first bit here in both these copies are seeing the same channel W minus. The second bits are seeing the same channels W plus. And now you can apply the polarizing transformation again, because you can take two channels which are identical and merge them or apply G2 to them. So that's what you do. You take the two copies of W minus and then feed those bits and apply G2, and the same thing here. Okay, so now you get a map which maps 4 bits to 4 output bits, and these 4 bits now see 4 different kinds of channels which have a natural nomenclature as minus, 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 plus, and so on, depending on whether you take the first bit or the second bit of the linear transformation. Okay, so you can probably see that by just here. Right, this U2 will be, you do a minus and then a plus, because here you have the second channel. Okay, so that's minus plus. So you get 4 kinds of channels, and now you can keep going. And then, of course, what is the actual picture here? You have 4 input bits transformed by this little butterfly-like 4x4 network, and then these bits now see 4 different kinds of channels. And now you can recurse. You can take the same network, 2 copies of it. So now we have 8 output symbols. And then you can once again do the same thing. You can take this first bit and match it with the first bit, the second bit with the second bit, and so on and so forth. And now you get an 8x8 map where the input bits are going to see 8 different kinds of channels. And if you actually think about what is happening, you have a single kind of channel at the rightmost part, at the output part. In one level, it splits into 2 kinds of channels, minus and plus. And then this is continued recursively, minus, 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 plus, and so on and so forth. You get the idea. So at the third level, you have 8 kinds of channels. At the nth level, you have 2 to the n kinds of channels. Okay, and these channels you can just number them as 1 through 8 or 1 through 2 to the n in general, and then just have this. All right, so that's the picture. All right, so let's so again, going back to this thing, you have an 8x8 map, and it has this nice butterfly structure. But for us, let's just, and actually this turns out to be roughly the Kronecker product of that basic 2x2 map 3 times. So that's an 8x8 matrix. So let's call it A8. And one can prove that the channels seen by these various input bits are exactly these channels you get in this tree. So the channel U1, the channel between U1 and all these outputs is W1. And then we'll abbreviate Y1 through Y8 by this shorthand. And the channel U2 sees, where you're given all these outputs and U1, because you're going to express this by this chain rule, that is exactly W2 and so on. And this requires proof, but it really just follows from construction and following the recursion that you can prove this. So basically, these different channels you see are exactly the channels you get in this binary tree of evolution of channels. Okay. And that's what Arıkan proved. So Arıkan proved that if you carry this process to depth D, a depth D tree, so that will give you 2 to the D different bit channels, W1 through Wn. And now if you think of this, and what Arıkan proved is that these channels have the polarization property. So what does that mean? That you can set any threshold gamma, and the fraction of channels which aren't within gamma of the 2 extreme values 0 and 1 is vanishingly small as n grows to infinity. And in fact, this gamma doesn't even have to be a constant. You can actually make it really, gamma can also fall rapidly with n. So the entropies are very close to 0 and 1 for most of the channels. So pictorially, if you and you can think of this just as an information theory thing, right? So you have this map and then this binary tree of channels. Most of the channels are going to have entropy close to 0 or 1. By conservation of entropy, the average entropy must always be the same, because at every step, you're just applying invertible maps. So the entire map from these n bits U1 to UN to the outputs is invertible. And therefore, by conservation of entropy, the fraction of red things, these highly noisy channels, must be roughly the entropy of the channel. And the remaining 1 minus h of W, which is also the capacity, will be green. So these will be almost noiseless channels. Okay, so basically this tree has this nice polarizing property. Very good. So far this is all seems to be some basic operations on linear. This just seems to be something about probability and linear algebra, right? So there's nothing about codes yet. So how do you get to codes? I'll come to that, but let's just quickly see this in action for a very simple channel, the binary erasure channel with erasure probability half. Capacity is 1/2. So let's see how the evolution is. At the root of the tree, you have one channel which has entropy half. if you apply this map once, so in this erasure case, there is a very explicit formula you can write down for what these two entropies are. So at the next level, you have two kinds of channels, which have entropy 3/4 and 1/4. Note that the average is equal to half. And the next level, you have this channel splits into two, this channel splits into two. So at level 2, you have 4 kinds of channel. And you get the idea. So each time, each of these channels splits into 2. But now you see that if you see some of this, so like this channel's worst channel overtook this channel's best channel. So some inversions happen. But you can keep continuing this. Level 4, you have 16 kinds of channels and so on and so forth. And this is just a exact computation of what happens in the tree. And you can see that if you go down to about length 1024, most of the channels are polarized. About half the channels have 0 and half the channels are 1, and there is some stuff in the middle. Okay, and that's really polarization in action. But you also see that even in this simple case, which channels are close to 1 and which channels are close to 0 is a pretty chaotic behavior. Okay, so even the simple channel shows a rich behavior. But the main thing for us is that about half the channels are almost noiseless. And Arıkan's idea is to get to codes from polarization is to simply use the noiseless channels for communication. Okay, so what do I mean by that? So I'll say something more about that. Okay, so how do you get to polar codes? So we have these n channels. Let's call the good channels as those channels which have tiny entropy, gamma. And by the polarization theorem, the fraction of good channels approaches capacity. Okay, this k by n is 1 minus h of w, which is capacity. So the idea is that we need to send k information bits. So we are going to place those, we're going to use those u sub i's to hold the information bits. And the rest we are going to freeze to 0. So let's illustrate this in the case of like 8 by 8 map. Suppose you have an 8 by 8 invertible map, and let us say that the good set of indices are 3, 5, 7, and 8. Just to illustrate this. So what then we will do is these are the green are the good bits. So those will hold information bits, and the remaining 4 will be frozen to 0. So when you have a 4-bit message, we will simply take the 4 bits. So we'll freeze the other bits to 0. We'll take the first bit, place it at U3, the second bit, place it at U5, and so on and so forth. Pad the rest with zeros, and then you just apply this invertible map. That gives you your code word. So that's how you encode. So once you know which indices are good, encoding is very simple. Okay, and for those who actually know Reed-Muller codes, what is really happening here is that we take this the same matrix from which the Reed-Muller code is drawn, the discrete Fourier transform matrix, and polar codes are picking some subset of those rows as the generator matrix. Whereas Reed-Muller codes will basically pick those rows which have the correspond to the lowest degree monomials. Right? But this one is a more complex information theoretic choice of which rows to pick. But it has strong parallels to Reed-Muller codes for that reason. And that's the encoding, which is easy. Now the decoding is the interesting part. So you'll need to, the channel outputs, you're trying to figure out what the bits UIs are. Well, the non-good bits are easy to decode because they are frozen to 0. So you just set those to be 0. Right? So when you're trying to, try to decode the bits in succession, 1 through n in this order. If a bit is not good, it is 0, so nothing to be done. If it is good, then you try to predict it based on the channel outputs and your prediction so far of the previous bits. And really what is happening here is that this is the channel which we analyzed, Wi. And now because these channels have very low entropy, there is a good predictor of the ith bit given this information, whose error by Fano's inequality is at most gamma. So we keep this, and therefore the probability that we make an error in any of these steps during decoding is at most the probability we make an error in any one of these steps, which is at most n times gamma, because each of these is very small probability of error. So if your gamma, the threshold of good channels, is much smaller than 1 over n, which can be achieved, then you are in good shape. So the chance that you make a mistake is very small. So this is really the framework of polar codes, and it achieves capacity because the fraction of good channels approaches capacity. There is something non-trivial about constructing the code, because constructing the code means finding these good channels. This is not trivial, but this can be done using simulations or other approaches, and you can also prove that these simulations converge. So you can get theoretical algorithms to construct it as well. And Arıkan showed how to encoding is very easy. It's just linear transformation. And further, it's a very simple linear transformation related to the Fourier transform. So it can be done in n log n time. Going to decoding, the main task is predicting the ith bit given the previous bits and the channel outputs. While this is information theoretically feasible, this could be computationally difficult in general. But in this case, because of, again, of the simple recursive structure, you can predict the maximum likelihood value of the bit efficiently, and the decoding can also be done efficiently. So everything is really pretty awesome. The one thing is that this statement of polarization is an asymptotic statement. And what we would really like to do to understand the speed of convergence is we need to understand how fast this fraction of good channels approaches capacity. So that's where the finite length analysis comes in. So what is the speed with which you converge? And to get inverse polynomial convergence to capacity, we need to say that the fraction of good indices is within some 1 over root, muth root of the capacity. Okay, and there where this mu is the scaling exponent I introduced in the early part of the talk. And this is what we established in subsequent analysis of polar codes. Okay, and again, these things also gave a value that the scaling exponent is at most 6, and this was further improved by Mondelli, Hassani, Arbanke to about 4.7. But you might remember that the optimal scaling exponent is 2. So now we are just getting greedy. Now that polar codes can achieve a finite scaling exponent for the first time, it's natural to wonder, can they go all the way and achieve Shannon capacity with an optimal speed of convergence? Okay, and that's the question. But here, there is some cause for pause, because the same paper which established this upper bound also said that it's unlikely that you're going to be able to prove a mu which is less than, say, 3.6 using this using the basic polar codes. So this suggested that the polar codes inherently seem limited, in the sense that while they achieve capacity in the limit, they cannot do so as fast as Shannon's theorem allows one to do. Okay, but that is for the basic polar codes. Now there are some generalizations of polar codes which one might consider, and which is what we also do. So one is, you can consider, this is all for binary input codes. Naturally, we are interested in non-binary codes. So that's one way to generalize, but that's not our focus here. But what we are interested in is that instead of the 2x2 map at each step, what if we applied a bigger map, right? So we had this basic 2x2 map, and that led to this binary tree of channels. You can literally replace this 2x2 by 3x3 map, and everything will go through as before. You will get a ternary tree, but each channel will split into 3 kinds of channels, and so on and so forth. Okay, the framework of polar codes is very general. So in general, you can have a L by L invertible map. Think of L as like a fixed constant, and the idea is that by picking L bigger and bigger, we're hoping to improve the scaling exponent towards 2. And then when you apply this map and you ask what is the channel seen by the ith bit given the outputs and the previous bits, let's give it a name Wi. So you have a single channel split into L kind of channels, and then you can recursively apply this and so on. Okay, everything is really the same. The whole game is what kernel to pick, how do you analyze it, and is it really worth it, and all those things. Okay, and all the results I said so far, both these upper bounds on the scaling exponent and this negative result, are for this binary alphabet and the simple 2x2 kernel. It turns out polarization is a very general phenomenon. So in work with these co-authors, we showed a couple of years back that you can take any kernel over any prime alphabet, and this finite scaling exponent can be shown. So the fact of polynomial convergence to capacity universally holds for all polar codes. However, here our main focus was to show that mu was finite, and we didn't try to optimize what mu was. And in fact, our bounds on mu probably got worse as you made kernels bigger. But here we're asking the opposite thing. Can you actually stick with the binary alphabet, but can you make mu approach 2 by making the kernels bigger? And indeed, this was done for the erasure channel. In these works by Fazeli, Vardi, and Yao, they said that if you make the kernel, for example, 64 by 64, you can get below 3 in the scaling exponent for the erasure channel. So those were optimized kernels and with some numerical computations. But asymptotically, Pfister and Arbanke showed that if you take the query alphabet, not the binary alphabet, but the query alphabet, then by making large kernels, you can make mu to be 2. And then in this very nice work, Fazeli, Hassani, Montelli, Vardi showed that you can actually get scaling exponent approaching 2 by picking larger kernels for the erasure channel. And what we do is really to generalize this result to not just the erasure channel, but really any binary memoryless symmetric channel. Okay, and this is the same result I've stated again. The only part I've added here to the previous thing is that you can get polar codes which have a scaling exponent approaching 2. And to do that, if you want to get a scaling exponent of 2 plus alpha, you need to pick a kernel which is sufficiently big compared to alpha. And then you can construct the code and do the encoding, decoding efficiently as well. So I must confess that the dependence of L on alpha is pretty bad. So really, this is at this point just a theoretical claim that you can achieve scaling exponent approaching 2. Okay, but the constants are not optimized, and those are interesting directions for future work. Okay, so that's the thing. So with that, I'll come to the sort of final technical part on how we kind of get to this. But are there any questions at this point?
Sorry, Venkat, what exactly is alpha again? This is something that you choose, and then the
yes. So you can choose alpha to be 0.1, for example.
Yeah.
And then my kernel will have to be some obscenely large constant, unfortunately, depending on 0.1. But it will be a constant. And so again, this O alpha here hides some constant factor depending on alpha in the encoding decoding tab. But that's right. So think of alpha as a small constant, say 0.1 if you want.
Yeah. Okay. Okay. Thanks.
Sure. Any other questions?
Hi, this is Chongming. A very interesting talk there. I just got 2 questions. The first is, how do you construct a kernel size that is larger than 2? Like, what kind of construct do they use? And how do we know whether those kind of kernel constructs are optimal?
Excellent. I'm going to address both of those questions in the next part. But a quick preview answer is that in the past, people have used kernels drawn as, like, for example, BCH codes or some algebraic codes and so on. In this work, the kernels, we don't have an idea exactly what the kernels are. We prove that such kernels exist by essentially a random coding type argument. And then once they exist, you can find them by essentially just looking for them, because L is finite, so it's a finite search space. Okay, so that's another reason the construction complexity is really not as ideal. But one could imagine using heuristics, just picking a random kernel and just going with it. But since we want a deterministic construction, we just prove the kernel exists and then go ahead and find it by brute force. But you'll see that in the next part. So.
Thank you so much. Then personally,
Sure.
Do you think the kernel size 2 by Arıkan, do you think that is optimal already?
No, the kernel size 2, I think, has limitations, like these previous work said, that they cannot get scaling exponent below 3.57 or something. So now if you use those codes and if you decode them by optimal decoding rather than the successive cancellation, then I do not know. That's an interesting question, but I believe for the decoding given by Arıkan, probably it's not going to be good enough.
Thank you so much.
Sure.
Venkat, is polarization rate is essentially what you're talking about, right? Is it the same thing?
So there are 2 things. There are some. So I'm talking about the speed of polarization. Okay. There's something else called the rate of polarization, which is unfortunate, but there are 2 things you can ask about, right? Yeah. What fraction of things are close to the boundaries? That is what I'm interested in here, the speed of polarization. You can also ask how close to the boundary are these polarized values? And that is often called the rate of polarization. And that is this quantity gamma, which I had in a few slides.
Right, okay, got it.
Right, and that is something like, for example, in Arıkan's original codes goes like 2 to the minus root n and something like that.
Right, okay.
So,
thanks.
So, yeah. Okay, so let's get back to our approach. So our approach is going to be to work with L by L kernels. Again, the picture is the same, the channel splits into L and stuff like that. And our goal is to show that you're within muth root of capacity, the number of good channels. And to prove this, it really just suffices to prove a strong polarization property. And actually, this goes back to now Mehul's question. So for example, it suffices to prove that the fraction of channels, once you go down deep in the tree, which aren't very close to the boundary, say within 1 over n square, is at most this quantity, which is the gap to capacity. So it is this quantity I call the speed of polarization. And this rate of polarization is often referred to as how close to the boundary values you are. And here I put n to the -2 just because it should be something less than 1 over n. You can really make this much smaller as well. So you can think of this as very strong polarization to the boundary values at fast rates, at rates which are inverse polynomial. And it's the speed of convergence is 1 over mu root, which is the primary focus here. So, all right. Okay, so how do we track this fast polarization? So you really don't have to worry about just, this is a more symmetric thing. You just have to understand capacity 0 or close to 0 or 1. For that, we just have a natural potential function. We take the entropy and 1 minus entropy. This should go to 0. And how do you prove that this happens with very good probability? For example, if you want to show it happens with probability roughly 1 over root n times plus alpha, so you track some sort of potential function. So note that this alpha is a small quantity like 0.1. So when you take the alpha root, right, this h times 1 minus h to this is like some high moment. So you're really controlling some high moment. And the way you can prove this is to really bound the expectation of this potential function for a random channel in the tree and then bound it. And then pretty much this quantity follows by some simple Markov arguments. Okay, and this is also the approach used by Fazeli et al. In the previous work. So we really just need to track this potential and prove that this goes down to 0 kind of rapidly. And to do that, and we won't need to do that for the full tree, but since the tree is a very local object, it suffices to do this for locally. So at some intermediate point in this tree, you're going to see some channel W prime, right? It could be some arbitrary channel, and we'll get to that. So it's an arbitrary BMS channel, and that will split into L-bit channels. And if you prove that on average, the G alpha of these channels, these L, the average value of these L things is about 1 over root L smaller than the one for W prime, then by just applying that recursively at every level, you get this 1 over root L to the D type decay. And this is exactly like 1 over root N because the length of the code is L to the D, right? For applying an L by L kernel, D steps of the recursion. So really the whole crux is this particular thing to show. How do you show this for an arbitrary BMS channel? And to show this, it turns out if you're going to show something this in a rather natural way, which is, so what are these channels? These channels are after all the entropy of these bits given the channel outputs in the previous bits. So we will show that for the first several of these indices, UIs, those bits are going to be very noisy. So the entropies are going to be very close to 1, which in particular means G alpha is very close to 0. And for the last things, because you're conditioning on lots of bits previously, the entropy tends to go down because you're conditioning on more stuff. And indeed, we prove that for the last several of them, almost capacity of them, these channels are almost noiseless. Okay, this is roughly the kind of properties we want to show for the overall map as well. And now we want to just show it for the local maps. And then there is a band of about square root L channels in the middle where we can't say much. So we just use the trivial bounds. And it is this square root L which leads to this 1 over square root L. So about 1 over square root L of the channels can be bad. So this is what we want to show. And how is this shown? It turns out in the binary erasure case, every intermediate channel you see is also a binary erasure channel. And that's really nice because the binary erasure channel is captured by a single number, the erasure probability, which is also its entropy. So you can actually prove a statement like this using known results about random coding and its behavior on binary erasure channel with some additional care and ideas. And that's what Fazeli et al. Did. They proved that no matter what the BEC is, if you pick a random L by L matrix, it will have a random kernel. It will give you these kinds of sharp transition behavior in the entropy where the entropy falls from 1 to 0 very in a narrow band with high probability. And then they were pretty much done in this framework. But unfortunately for us, if you start with even say the BSC, after one level of the polarization, you will get more complex channels. So the intermediate channels get much more complex with humongous alphabet size. So they don't have any simple description or common behavior. So we are unable to prove that a single kernel will work universally for all the kinds of crazy channels which might arise in this process. So how do we get around this? We use different kernels. Okay, it's just a natural idea to try. So for example, illustrating this Arıkan construction now for the 3 by 3 case for 2 levels of recursion, So you have 3 bits applied to the kernel, then you take the red bits, which are all the same, you mix with this kernel and so on. So then you get a 9 bits mapped to 9 bits. In the tree, this is what happens. You have W splitting into 3 channels, then each of these splits into 3 channels and so on. And every kernel is the same. And what we are proposing is that, for each of these steps, let's use a different kernel, right? So essentially, this tree still remains the same, but exactly how these channels depend on the parent is going to be different at each node because you're using different kernels at every point in the tree. So that's what we need to see. So for each channel which you get in the tree, we will find a kernel which sharply polarizes it, and then we will use it. Okay. So this is our main theorem, a technical ingredient, which is give me a channel, BMS channel, and I'll give you a kernel which has the sharp transition probability, in the sense that if you look at those L channels, the first several of them have entropy very close to 1. The last several have entropy close to 0. There's a small band of root L in the middle, which we give up on. And this implies our desired kernel. There is still some caveat that this really only works when the entropy of the channel W prime itself is not very close to 0 or 1 already. If you're already pretty close to 0 or 1, then this runs into some trouble. So in that case, we go back to the Arıkan kernel itself, and we simply tensor that log L times. So we think of L as a power of 2, and then we will use that. And Arıkan's kernel is known to have something which we call very fast suction to the extremes. Once you are pretty close to the boundary values, it really sucks you to the boundary values very quickly. So this is the property Arıkan's 2x2 matrix has. So we just pivot to that. Okay, so then the whole game then becomes analyzing these random kernels. So let me tell you a couple of things about this, and then we will wrap up. So again, the picture is this. You have some channel W prime. We have a random, okay, and I should have said that how do we get these kernels? We get these kernels by picking a random map, and we prove that the sharp fall in entropy happens with high probability. Okay, so we take a random kernel, and we want to say that these bits look extremely noisy, and these ones are almost noiseless. So how does the framework for analyzing that? So there is a very simple but nice connection to analyzing random linear codes. So let me visualize that. So really, you should think of this U and X as row vectors, but for picture, I've just drawn them like this. So what are you doing? You're taking an L by L matrix and transforming U. You get X, send it on the channel, you get Y. Okay. So now what are we interested in? We are interested in predicting this ith bit given these previous bits. Since we know all these bits, let's mark it by blue. And remember, this is a row vector. So once you know the first I minus 1 things, you also know the first I minus 1 things, how they are transformed by this. So I'm going to shade that out as well. And then if you just a moment's reflection, you can convince yourself the whole picture now just becomes, you can forget about the first I minus 1 rows here, and you have a k bit vector where k is just L minus I minus 1. And predicting UI, given all these previous bits and the channel outputs, is really the same as predicting the first bit of this message B, a random message B, when it is transformed by, you can forget these rows, the last k rows of this matrix, and then you get a code word which is then sent on this channel. So this V is a message, and this bottom part of K is like a random linear code because it's a random K by L matrix. Okay, so this requires a moment's thought, but really it's more or less like, at least I hope the pattern matching was clear. So somehow understanding these channels, which we need to understand, really then becomes understanding how can you predict the first bit of a message when it's transformed by a random linear code. So that's what is written here. So now G is a random linear code. This is a generator matrix, K by L. You transform a K bit vector by this. The entropy of the ith channel is simply now, how well can you predict the first bit given all the outputs? And what is this? How does I come into the picture? The dimension of this code is exactly L minus I plus 1. So for the initial values, when I is small, this is a very high rate code. So we expect you shouldn't be able to do well because it'll exceed capacity. When I is very big, this is a very low rate code because K becomes small, and then you should be able to predict this bit well. And indeed, that's what happens. So we really need to show that when K is large, so large rate code, you cannot predict the first bit at all. And when K is small, you can predict it very well. And this jump happens in a very sharp band. But this really follows I mean, this at least in spirit follows from what you would expect for random linear codes, because if you take a random linear code, we know, okay, what are the facts we channel output. If your rate is not too big, if it is like the capacity minus 1 over root L, then you can really predict this bit very well, which means its entropy is tiny. This pretty much follows from Shannon's theorem, because Shannon's theorem says that if you operate below capacity, you can predict the entire message very well. In particular, you can predict the first bit very well. The other part we need to show is that if your rate is kind of big, if it's capacity plus root L or 1 over root L, then you really cannot predict the first bit at all. It's almost uncertain. It's almost 50-50 random. And this is really a very strong converse. So we are saying that at rates above capacity, your first bit is extremely unpredictable. And this strong converse is really the key technical ingredient. So what we really show is that we show extreme unpredictability. So the entropy is very close to 1 of even a single message bit the moment the rate goes slightly above capacity. And while strong converse theorems are, of course, known in information theory, what makes it difficult quantitatively here is that both these quantitative aspects are very crucial. That the converse should kick in the moment you exceed capacity by 1 over root L, and also it's a strong converse in the sense that it says you can't even predict the first bit of the message, and you really cannot predict it at all, better than 50-50. And note that I should also say this is really applies only to random linear codes, because if I just want to predict the first message bit accurately, I can just repeat it 10 times and send it to my code word. I'll get good accuracy. But the point is we are talking about random linear codes, so this doesn't work out. So
Venkat, why? Sorry, why doesn't this? So you mentioned that for the first part, just essentially the channel coding theorem kicks in.
Yes.
But the second part, why doesn't the converse of the channel coding theorem kick in? The strong converse.
So the converse of the channel coding theorem will kick in, but it will not give you good. What will the converse theorem say? The converse theorem will say that you cannot predict the entire message with, with high probability. Here we want the first bit.
Okay.
So this implies the converse. That's a great question. That's exactly the point. The strong converses do kick in at rates slightly above capacity, but they don't give you this extreme unpredictability. I believe there are also other converses which can give you this extreme unpredictability of the first bit, but then they will only kick in at a fair bit away from capacity. So here we want both of these things together.
Okay, thanks.
And that's what makes it tricky. And it's important to get these quantitative bounds for our result. And so I'm going to skip the proof idea in the interest of time. But really, first we prove it for the BSC and using some symmetry properties. So it really, it's a bit of work, but we prove it for the BSC first. And the main thing we use is that once you go above capacity, if you take a typical received word, when you send 0, that is more likely to have come from some non-zero code word as well, just because you are above capacity. And so we kind of use that and somehow compare two codes, one of which is one dimension 1 less than the other, and prove this result. So that's for the BSC. And once we prove it for the BSC, we use the fact that any general channel is a convex combination of BSCs, and we somehow discretize it, reduce its alphabet size, and so on. So it's a lot of complex and delicate calculations. We prove this result. Okay. Now, when you want to construct this code, there are some additional challenges, because these intermediate channels for which we construct kernels, they have huge output alphabets. So we cannot even like represent them, let alone work with them. So we really have to work with the quantized approximation to them. And then we will find a kernel for those approximate versions. And then we have to just argue that those kernels will still work fine for the actual channels seen by the decoder. Okay, so this is some thing we have to balance. And this somehow doing this in a straightforward way will restrict us to achieve only inverse polynomial decoding error probability, because we have to quantize suitably. For better bounds, we use additional ideas, in particular ideas from a very nice work by Wang and Dursma, who proved results similar to ours for other alphabets as well. And in fact, with the sharp rate of polarization as well, in addition to the speed of polarization. Okay, so I think that's come to the end of the talk. So essentially, we show that you can achieve you can approach capacity within epsilon with a block length of about 1 over epsilon square, which gives you the almost optimal speed of convergence to Shannon capacity. And we can do that with linear codes, which have an efficient encoding decoding algorithm. And to do this, we changed the polarization framework somewhat. We went from the 2x2 kernel to large kernels. And more significantly, we went to different kernels at different parts of the construction. And these kernels are carefully constructed to match the channels you see in the decoding. And to analyze and make this all work, we had to prove a strong converse for bit decoding using random linear codes. Okay, and that guaranteed the necessary kernels, which we can then find by brute force. Okay, so natural further work would be to extend this to non-binary alphabets and also improve the decoding error probability we get. And both of these is achieved in this work of Wang Duursma. I believe the construction aspect of the codes is not completely adequately addressed here, but these extensions are really quite amazing. And there are many challenges. So one thing is that for the BEC case, you had a single kernel. You could prove that a single kernel will just work everywhere in the tree. Here we had to mess up the construction with different kernels. It'll be nice to know if that is inherent or somehow avoided. And throughout, I have said that a certain fraction of channels are good, and we want that number to be large. But the question is, how do you find these channels? And as I said, we know how to do this, but to have a better analytic understanding of which channels are good would be very nice. And like, as I mentioned at some point in the talk, polar codes, at least Arıkan's original version, are drawn from the same matrix from which Reed-Muller codes are picked. And there is really a lot of striking similarities. So there's been a lot of hope to make progress in the question of whether Reed-Muller codes achieve capacity using polar codes. There are many intriguing results, but we still don't know the answer to that. And as I said, polar codes are the only known codes so far with finite scaling exponent. It is believed that spatially coupled LDPC codes might have this property, but I think proving that is another matter, and there seem to be significant obstacles. It'll be great to resolve that. And I also feel that this application of the strong converse we prove seems like a very basic fact about random codes. So I feel it might have other applications as well, and it'll be great to find this. And I just put one of them, which came into mind. There's been a line of work in theoretical computer science on understanding time-space trade-offs for learning problems, and very tight results are known for learning parity. But when you add noise to the mix, we don't know the right results, and maybe these converses holds at least the information theoretic key to how to make progress on those things. All right, I think that's all I have. Thanks for your attention.
All right, so thank you, Venkat, for a very nice talk. Yeah, so if you have any questions, please feel free to type in the group chat and I will unmute your mic. Well, so while people are typing in their questions, I have a few questions. I think you mentioned about how L scales with alpha. Okay, can you elaborate more on that? Is it exponential in alpha? Or?
Oh yeah, L is unfortunately exponential in alpha. Yeah.
Okay, sure.
Yeah.
Sure.
Because you get this L to the minus log L we get, and then that should be roughly like L to the alpha. So you want log L to be alpha. So that's what I said. It's unfortunate, but we don't know how to improve that. So
okay. Another question. Oh, sorry.
Sorry, what's L? Is it the kernel size?
Yeah, the kernel
L is
size.
the kernel size. Yes, L was the kernel size. Yeah.
Okay, thanks.
Yeah. So is it necessary that the L be constant throughout your kernel polarization?
Yeah, I mean, for us, the way we do it, yes, because we are really finding L by L things by brute force. But it's a good question whether once you, I mean, maybe once the channel becomes very good, you could, yeah, I mean, some parts might be for just structural simplicity because, for example, we say that if the channel is already noiseless or noisy, we just take the Arıkan kernel and tensor it to the log L power. So perhaps there we can go for a bigger kernel. But it will sort of mess up the construction symmetry, right? So because we, right now by using L at every stage in parallel, we get this nice behavior. But if you mean whether you can make L gradually bigger, I don't know. I mean, the question is how do you guarantee a good kernel exists then?
I see. Yeah. Okay. So one final question.
But it's a nice question. Yeah, I think it's definitely worth some thought on whether you can slightly work with suboptimal kernels once they are big enough or something.
Yeah. Okay. One final question before I let someone else ask. So once you find your method was basically to randomly construct a kernel. So to verify that the kernel works, is it efficient?
Yes, it will be efficient, but again, in a theoretical sense, because you can really just compute all these channels, because you have a fixed channel in mind. That's why we need to quantize. You compute everything and you just check that it works.
Okay. So,
but this is why I said that, for example, the construction issue is important, because if you just prove the kernel exists and the channel is not compactly described, then you're in trouble. So we kind of go through a lot of pain to show how we can quantize the channels and yet kind of compute good approximations.
Okay. All right. So we have Li Chen from Sun Yat-sen University. Yeah, you can go ahead and ask your question.
Hi, Venkat. I think you have delivered a nice talk. I have a couple of questions. My question is really to how strong the conclusion can cling to the setup of the channel. I think there are two in here. For example, how important is the setup of symmetry of the channel? If you don't have a symmetry for the channel, would you have a very different conclusion in terms of your convergence speed of polarization? For example, the scaling exponents. This is one. The other one is how important is binary input? As I understood, I do recall some work earlier that says if we are having a non-binary kernel, we probably would get a better polarization speed. I'm not sure, but I'm not sure whether it is in terms of the scaling exponent or in the error exponent, but one of the property, or maybe both, they are better than binary kernels. So in this case, if you're having a non-binary code, then this sort of disconnect me with the earlier polarization setup where you have two inputs and you polarize the entropy in your setup. I think, but however, in other polar code papers, for example, Arıkan's paper, they talk about mutual information, but I think they could be equate. But anyway, so if it's not non-binary kernels, then would that be a different story in terms of getting?
No, so first, let me answer your second question. The non-binary, I mean, we focused on binary just because, I mean, it's already like a rich enough case, and it's the most well studied, and it was really just to focus on something. And of course, working with QRE poses additional technical difficulties, but there was nothing in our framework which we thought would not extend to QRE case. And indeed, this work of Sinpo Wang and Ivan Duursma works for general non-binary things. So they show how to work for non-binary things and get scaling exponent too. So I don't think the non-binary thing is any change. It might make some of the ingredients more technical and so on. And indeed, in our previous work where we showed that the scaling exponent is finite, there also it was a little more. It required some new ingredients, and but ultimately it worked for prime alphabets just the way it worked for binary alphabets. Now, the question about symmetry, it's the thing is that if you want, since we are focusing on linear codes, focusing on symmetric channels allows us to just talk about channel capacity. If you don't work with symmetric channels, you can still achieve the symmetric capacity using these ideas, pretty much automatically, because it can be achieved by linear codes. And I mean, the only thing is that for these in-between channels, I mean, there might be still some things to check, but I suspect it should not be a problem. But I think even for non-symmetric channels, and even, but there are some extensions which do some non-linear part to work with non-symmetric channels as well. So I believe that by now, even that is not such a big deal. And I think there are parts of this Wang Duursma paper which also work for non-symmetric channels. They really just work for any discrete memoryless channel.
Well, during a talk, I have been trying to identify the symmetry elements in the whole analysis, but I couldn't find. But I'm not really sure if it is not symmetric, then perhaps your our analysis would become more challenging. That's my one suspicion.
Yeah, so one aspect where we use the symmetry is, for example, we said that the in-between channels are convex combination of the binary symmetric channel, right? So there we certainly are, this converse theorem which we prove, we are doing it for symmetric channels. So at least the way we do it, we seem to be tied to that. But as I said, I don't think it's inherent. I think there are workarounds for non-symmetric channels, even if you want to get to capacity and not just the symmetric capacity. So, but that's a good point you raise. If you ask whether our result works and gives symmetric capacity for an arbitrary channel, that's a good question. And I thought it would, but now I'm not 100% sure. Yeah.
Okay. One final thought that I would like to share with you. I was quite impressed by what you have given in this sentence. Give me a channel, I'll give you a kernel. I think that is exactly what we are vindicating. Shannon has proven in the channel coding theorem more than 7 decades ago. In his proof, and he hasn't assumed any sort of structure in terms of the code. And what he has assumed is if you can have a code that could match the channel, for example, you can optimize the distribution of your input, you can really achieve the capacity. I think this is what we coding theorists have been discover after 7 decades, that really, if you need a good code, the code does need to match the channel. I think what the sentence you gave just now is exactly what Shannon assumed more than 7 decades ago.
Right. Yeah. Of course, there has been recent works which try to talk about universal channels and stuff, and that is also interesting. And in fact, one of the considered drawbacks of polar codes is that exactly this, that if there is a channel mismatch, it's not clear how well they will perform. So there has been works trying to talk about universal versions of polar codes, but yeah, I mean that can also be desirable, but that's not what we do. Yeah, certainly.
Yeah, in fact, in the modern codes, polar codes, LDPC, and turbo, we classify them as modern codes. Among those 3 coding schemes, polar is the only one that is trying to match the expression of the code to the channel. But the other 2, they are not matching to the channel. They are winning because of the random property. That's another assumption of Shannon's proof. Now, this to match the channel is what polar code is winning, in my opinion.
Yep.
Thank you.
Thanks, Ian. Very, very nice perspective and questions. Thanks.
All right, thank you. Any other questions?
Can I ask a question?
Yeah, sure.
Yeah, so it's still related to the channel models considered here, because the channel model considered here is memoryless and symmetric. And so for some practical channels, for example, I'm working extensively for channel coding for data storage systems, right? So, so for data storage system, many channels have memories, and also the channels are data dependent. So, are there any ideas and guidelines on how to construct kernel or how to construct efficient polar codes for those kind of channels, which are have memories and also data dependent,
So this has also been looked at in many works, and including we also have some work on basically polar coding for hidden Markov models. So you can, if you assume some channel is given by some Markov process, and you don't observe the channel state, so we prove how to code for these things, and we get polynomial code length in both the mixing time of the channel and the gap to capacity. So I can point you to that work as well if you're interested.
How about if the channel is data dependent?
Data dependent. So what do you exactly mean by that in the sense?
So for example, it may introduce some interference to the channel, and the interference is data dependent. It depends on the input data pattern.
Oh, okay. So it's not additive, you mean?
No, yeah.
Yeah. So Yeah, in general, the channels, I mean, so in the memoryless case, people have definitely considered very general channels. It doesn't have to be additive or symmetric, as I said.
Yeah.
So, but whether you can mix hidden Markov model and this, I don't know. So, but let me at least point you to this paper. I'll post it on the chat. And I think there are some other works as well. So,
okay.
This is one paper we had. So this is the one I know best, but others have looked at this question as well. So.
Okay, thank you. Yeah.
Interesting.
We state these things in terms of compression, but it also works for coding for noise caused by these hidden Markov models.
Okay, thanks.
But again, here our focus was more getting a finite polynomial convergence. We didn't optimize the thing, the speed of convergence and so on. So it's natural to consider that.
But what by my understanding, the code constructions are done by offline, right? So
code constructions are done offline, yes.
Yeah, so the computational complexity for code construction, I think, is, strictly speaking, not so critical, right?
Yeah, I mean, at least, I mean, there may be elements of this. As I said, there are many other works which have looked at it too, and then some of them seem to use practical approaches. I mean, here our focus was primarily proving the theorem we were after. So, and indeed, here the code construction time is not optimized for practicality, but yeah.
Okay, so at least we need to ensure the complexity is practically affordable. Yeah, and then
so yeah, but there may be ideas in these or other works which you can perhaps use, right? So even if you cannot quite prove that they have the necessary properties, they might still work fine in practice.
Okay. Yeah, I see. And another issue is that I think regarding the decoding of polar codes, I think the decoding capacity of polar codes is fine. And for many applications, it's comparable to LDPC decoders. But the decoding latency is still a big issue. Because latency,
I believe that's why, like, even in 5G, it's used more for control information because those tend to have shorter lengths. And but on the other hand, they can operate for smaller lengths and also give. They're pretty good at low rates, which you can afford for the control information.
Yes, that's right. And also, for example, I'm looking for channel coding for non-volatile memories. And so the error rate performance of protocols can be very good, but decoding latency is not affordable for many applications like memories for edge computing and etc. It seems it's still a bottleneck and it's a very fundamental problem.
I think one issue is also parallelizing the decoding, right? So because it tends to be sequential, that's a drawback. Whereas things like LDPC, you can run these, even though it takes more energy in many iterations. Each iteration runs in parallel. But I've been told that there are heuristics to run a lot of these decoding steps simultaneously to get at least some modest parallelism in the polar decoder. But I'm not.
Because as long as the decoding is carried out in a successive fashion, so the latency is unavoidable.
Is a problem, So at least if you do it the way it is described, normally it would be a problem. But perhaps again, one can do some heuristics to decode blocks of bits at a time and speed it up a little bit. So, but then you will suffer and you will lose a little bit in the miscommunication or block error probability. But maybe that's affordable if your rate is low enough. So.
Yeah. Okay. Thank you.
Yeah. Thanks.
Sorry. Okay. So, any more questions?
Oh, hi, Venkat. It's a great.
Oh, hi.
Yeah, it's a
thanks.
It's very clear the introductions of the polar codes. So I have one question because I'm doing the works for deletion and insertion correcting code. Yeah, so I'm just a bit confusing, like how the polar code can be applied to correct deletion and insertion, because, for example, the input data you have some for the very noisy channel, you just have the 3 bits, right? You put all the things to be 0.
Yes, yeah.
For example, the deletion and insertion channels, if the output you have some deletion or insertions, then how you can distinguish the free bit and those who are information bit?
I don't know. So I know there have been works on trying to apply polar codes to deletion codes, and indeed I looked at one of them, which I think was by Alex Vardy and others. Yeah, but I didn't somehow get very far. I didn't get a good grasp of what was going on. So, and it also seems to have some connections to the other question which was asked by Kaiku on these hidden state things. They also seem to, because if you decode the first half and the second half, like how many bits you have received in the first half is some sort of random state. And but yeah, I don't have a good answer to that. I feel like it doesn't seem like a good fit at all to these insertion deletion codes. On the other hand, there are papers which are looking at it. So clearly there is still, I think by being clever about how you use it, maybe there are ways to use it. So.
Oh, okay. Another question is here I see the further work is extension to non-binary alphabet, because I'm also working for DNA storage. So it's a quaternary alphabet. So,
yeah.
I'm thinking is it hard to extend from the binary to quaternary, or in general non-binary? Because I think we can, for example, we can change the alphabet, for example, the quaternary to binary, right? Using just the binary representations of every symbols.
Right, but the thing is that will change the capacity, because the action of the channel may not respect your representation as bits. And in general, I would say it's not hard for any conceptual reason. The overall framework is going to be same, but I think the technical obstacles for non-binary things can be harder, right? Just because, you know, it just is a richer space. But and in fact, I think the construction for non-binary really proceeds in the same way as our blueprint, right? With these higher kernels and everything. But you just have to prove these theorems, for example, the kernel matching the channel for non-binary alphabets. And that could be tricky. So.
Oh, okay. So. Okay, I see. Okay. Yeah, just one more thing, but it's not the question. But I think the student that Hanmao mentioned in the beginning of the talk, I think it's me.
And not just you. Okay.
Okay. Yeah.
When I write my thesis, yeah.
And I read your thesis. I don't know if I read mine, but
oh no. The thesis that Hanmao recommends to me is your thesis. Yeah.
Okay. Okay. So to all students here, yes, please, please go to Venkat's website if you are starting to write a thesis. Yes, that's how you should write a thesis, or in fact any paper if you want. Okay, any other questions? Okay, actually I've yeah, okay, let's not, yeah, a few more questions, but let's not hold our speaker back. So with this, let's end our seminar series, our talk for today. Let's thank you, our speaker, Professor Venkatesan Guruswami from CMU.
Thanks a lot, Hanma, and thanks everyone for your attention and great questions. Yeah.
Okay. So a little bit of admin for next week. Next week, our talk will be delivered by Professor Raymond Yong. Am I right? Yeah.
Yes.
And yes. Okay. It won't be at 9 a.m., but it will be at 5 p.m. Singapore time. Okay. So this is unearthly for the States, but yeah, more earthly for us.
Sorry, Venkat.
No worries. Yeah. Yeah.
All right. So yeah. So I hope to see everyone next week. Okay. Again, let's thank our speaker for giving this wonderful talk.
Yeah. Thanks everyone.
Thank you. Yeah.
Have a good day.